Hi, I am Vishwajit Sharma, and in this video we will talk about the continuity equation, and we will try to go inside this concept, and we will derive the continuity equation in partial differential form and also in vector form. Coming back to this, let us assume a very infinitesimal small control volume. So this is the control volume in red color. You can see this is in cuboidal form and its size is very small, and the dimensions can be written as this is in x direction, so this length we can write as dx, this is in z direction, we can write it as dz, and this is in y direction, we can write it as dy. So these are the dimensions in the respective axis. This is in rectangular coordinate system. So we can write as the volume. So what will be the volume of this cuboid? The volume of this cuboid is the dV is equal to dx, dy and dz. Okay, so this is the control volume, dx, dy and dz. Now what does the continuity word says? Continuity word says that whatever energy or matter which is coming inside the system, here our system is this control volume. So whatever the energy or matter is coming inside this control volume, that should be equal to the total matter or energy going outside the system, unless until there is nothing generated inside this control volume. So if some generation or if some source or sink is present inside this control volume, that means something is generated or something is exhausted or consumed inside the control, then the mass or energy which is coming inside this control volume plus which is generated or exhausted is equal to total outside the system. So in continuity we are mainly focusing on m dot. M dot means mass per unit time, that is the mass rate. Now continuity equation can be written as the mass m dot. We know that mass is mass, m is equal to density into volume. We know that mass is density into volume. So what is m dot? Or we can write it density into area into x. This is the length dimension. Okay, so we can write here as m dot is equal to rho volume divided by time is equal to rho into area into x divided by time is equal to rho into area into velocity. This is the velocity, not volume, velocity. Okay, in respective direction. So first we will talk about in direction x. Let's assume that in x direction, what is the face? Face is this yz. We can say that this face, this face. Some mass is going inside and some mass is coming out from it. Okay. So what is the mass rate which is coming inside this control with this yz side? So we know that the mass rate is rho into area into velocity. Okay, so here we can write as what is the area. Area, you can see this is dy length and this is dz length. Okay, so we can write as that m dot in x direction is equal to rho into velocity is u in x direction velocity is u into area. Area is dy into dz. So this is clear. We have mass in equal to rho into u velocity, u component of velocity in x direction into area. Area is dy into dz. So this is clear. Now we will talk about what is mass coming outside. So what is mass inside? It is rho into u into dy into dz. Dy into dz. Okay. This thing. Now we will talk about that what is going outside. So whatever is going outside, that is this mass, that is equal to this mass and some change with respect to dx. You will get to know that m dot out in x direction, what is coming outside is equals to this one, rho into u into dy dz plus change in this with respect to this much length. So what is the change? Equal to del of this total, rho into u. So we can keep outside dy dz upon with respect to del x. So we have to write here as dx. This we can write as rho u dy dz plus, we will write z as this, plus del rho u upon del x into dy dz into dx. Okay, so if we take dy dz as common, so we can write it as rho u plus rho u, dy dz as common, so we have read del rho u upon del x into del dx. So del of rho u del x into dx, and we have dy dz. Okay, this is clear. So I am writing this equation here. First we should write here, it is rho u plus del rho u del x into dx dy into dz. Okay, so we will just remove this one and we will write directly this here. We will write directly this one. It is equal to rho u plus what is del of this rho u upon del x into del x is extra term, so rho is same, del x is extra term, so we will write as dx, and what is common? Common is dy into dz. Okay, dy into dz is common term. So we have m dot in as this, m dot out in x direction is this, so we have overall m out minus m in, m dot out minus m dot in x is equals to this term minus this term. So we have rho u plus del rho u upon del x into dx minus of rho u. So dy dz is common, so this rho u will be minus into dy into dz. So this rho u is cancelled out. So we have del rho u del x into dx dy dz. So m dot out minus m dot in y is equal to del rho v upon del y dx dy dz, and m out minus m dot in z is equal to del rho w upon del z to dx dy dz. So this term is here. We can add all these three with some change inside the system. So we can write as the continuity equation as continuity or mass conservation. Mass conservation is, it says like m dot cv plus m dot out minus m dot in cv is equals to, it is generation like, okay, it is something change, is equal to change is equal to 0. So it is del rho by del t into dx dy dz. Okay, mass is equal to density into volume, so upon delta t is m dot. Okay, plus if we combine all these three, means if we can write it as 1, this is 2, this is 3. So m dot in of control volume is 1 plus 2 plus 3. So if you write 1 plus 2 plus 3 dx dy dz, dx dy dz, dx dy dz, this will be common. So we have this 3 term. What this term? The common term will be del rho u by del x plus del rho u del y plus del rho u del z and the common term is dx dy and dz. Okay, so common term is this one. Okay, and this should be equal to 0. Now if we take common dx dy dz, then we will have this. And if we take out dx dy dz common from this first term, from second term, then we will have del rho del t dx del rho del t, oh, this is common, plus del rho u del x plus del rho v del y plus del rho v del y plus del rho w del z equals to 0. So this is my continuity equation. It is applicable for all type of flow in any coordinate. This is applicable. If you talk about this flow, like it is also applicable for compressible or incompressible flow. It is applicable for both. If we talk about steady or unsteady flow, so it is also applicable for these two equations. And if we talk about viscous or frictionless flow, frictionless or inviscid flow, so it is also applicable for this one. Now we will try to write this equation in different form. Okay, we'll try to write this equation in different form. I am also sharing this notes in the description box. You will get the link, and from that link you will get the notes. If you have any confusion, then you can ask me. You can mail me. Mail will be also given in description box. If you need more from me, then also I can help you with that. So our final equation, continuity equation is this. So in first case, if we talk about steady, so for steady, this time term will vanish and it will give like del rho u del x plus del rho u del rho v del y plus del rho w del z equals to 0. So this equation is actually about steady flow. If we talk about incompressible flow, for incompressible flow, we will have this change in density is 0. So because density is constant is incompressible flow, so this term will 0 and it will be like same. So and also this density, since this density is constant, it will come outside of the bracket, and since this term has been vanished, so we can only write del u del x. So it will come like del u del x plus del v del y plus del w del z is equal to 0. Okay. Is 0. We will try to write this equation in the operator form. So we will write as, we know that we have one operator is this gradient operator. Okay, you have seen this gradient operator, reverse delta. Okay, reverse delta, this means del del x I cap plus del del y j cap plus del del z k cap. Now this velocity form, we know that it is ui cap plus vj cap plus wk cap. We know that velocity is always written like this, and this reverse delta is written as. So what is gradient operator? Gradient operator says that del dot v means gradient operator is the dot product of these two. So dot product is the scalar one, and only the scalar form, this two coefficient will be multiplied. So we can write as I cap will, I dot I is vanished, only del u del x plus del v del y plus del w del z is equal. Okay. So here we can write as incompressible equation, we can write as, okay, this v is this one. So the overall equation we can write as, final continuity we can write as del rho by del t plus gradient of rho v is equals to 0. This is dot product. Okay. So this was all about the continuity equation. If you have any doubt, so you can contact me with my mail ID, which is given in the description, and also I request you to download the notes and see it, and if there is some mistake, so you can also call me out, you can tell me, and if there is an area of improvement, so you can also your suggestions are also welcome. So this is all about from me. I will meet you in next class with some different concept.